So the next type of problem that we're going to perform is one that asks us what is the concentration of a particular metal cation in solution after the complex ion has formed. And the example that we're going to look at is silver. So we can ask the question that what is the silver plus concentration in a solution that is initially 0.05 molar silver plus and 0.05 molar Cl minus in aqueous or in 3.0 NH3. So what's happening here, and the reason that we have to use such low concentrations for silver and chloride, remember that silver chloride is very, very, very insoluble. If I take a solution of silver chloride, mix it together, we're going to get a lot of precipitate. But in that supernaut liquid, there's going to be some silver ions floating around, and there's going to be some chloride ions floating around. The question is, how much can we remove all of that silver by adding concentrated ammonia? In these particular problems, we're going to have a lot of instances where, since you have a complex ion that has either 4 to 6 ligands in some cases, there's going to be a lot of exponents involved. So to get rid of any type of polynomial type equation, we usually employ a two-step approach that might not seem rational at first when you're first doing these problems, but it's going to be the best way to solve these. So we're going to do 2 steps, and the first step we want to look at is the reason we look at it in 2 steps is twofold. Number one, since the Kf values are so large, we can assume the initial complex ion, or the initial complex ion formation, goes to completion. So initially, we look at the Kf table. We see that silver can form a complex ion with ammonia. In this case, we have silver plus 2 NH3s is going to form Ag NH3 2 with a +1 charge. On the Kf table, it lists this entire reaction. So the Kf table tells us 2 things. It tells us, number 1, a complex ion will form. And it tells us, number 2, how many ammonia ligands are around that central atom, in this case, silver. So if we assume that this goes to entire completion, we have to think about the reactions we talked about back in chapter 3 and 4. And we can say initially we have 0.05 molar silver, we have 3.0 molar ammonia, and we don't have any complex ion formed yet. If we assume this goes all the way to completion, the change in concentration will be dictated by the limiting reactant. For every silver that reacts, we're going to need 2 ammonias to react with that. So the limiting reactant, since it's a 1-to-2 ratio, is definitely going to be the silver in this case. So the change in concentration is going to be minus 0.05. That tells us after this reaction has completed, there's going to be 0 silver plus ions in that solution. The change in concentration for the ammonia is going to be 2 times minus 0.05. That tells us that after this reaction has completed, our concentration of NH3 is going to be 2.9. When 0.05 moles of ammonia interacts with 0.10 moles, when 0.05 moles of silver interacts with 0.10 moles of ammonia, we're going to form 0.05 moles of the complex ion. So this assumption right here is based on the fact that everything is going to form. We have a really, really high value for K. That tells us that this reaction is going to favor the products. So it's going to go forward, but it doesn't go forward 100%. There's going to be an equilibrium established there. So we need to take these concentrations right here and set up an equilibrium, or look at the dissociation of this complex ion in solution. So that's going to be our second step. So step number 2 is going to be use the concentration from step number 1 and the Kf to determine the equilibrium concentrations. And the equilibrium that we're going to look at is Ag NH3 twice with a plus charge, which is our complex ion that formed, and it's going to be in equilibrium with silver plus in aqueous solution plus 2 NH3s. This equilibrium constant is abbreviated by Kd, which means it's a dissociation constant. And the Kd is going to be 1 over the Kf, or 1 over the formation constant. For this particular reaction, the Kd is going to be equal to 6.3 times 10 to the minus 8th. So now we can look at an ice table, and the initial concentrations are going to be the concentrations from that first step. We know that we have 0.05 molar in the complex ion. There's going to be 0 silver present, and the ammonia concentration is initially 2.9. We're going to allow this to reach equilibrium. So we're going to have plus X for the silver and plus 2X for the ammonia, and then minus X for the complex ion concentration. So our equilibrium concentrations are going to be 0.05 minus X for our complex ion, X for the concentration of silver, and 2.9 plus 2X for our concentration of ammonia. We can now set up the Kd expression, and that's going to be equal to the concentration of silver plus times the concentration of NH3, that quantity squared, divided by the Ag NH3 twice plus 1 complex ion. If we plug in our values, it's going to be X for the equilibrium concentration of silver, 2.9 plus 2X for our concentration of the ammonia. We also need to square that quantity, divided by 0.05 minus X for our concentration of our complex ion. This is going to equal 6.3 times 10 to the minus 8th, which is our dissociation constant. I want everybody to think about what's going on here, because the most common mistake that students make when performing these types of calculations are that they will forget to square this value. So put a little asterisk next to this, and this is the most common error. And on a multiple choice exam, I can assure you that if you didn't square that number right there, I will certainly pick that as one of the other choices on your exam. When we're dealing with complex ions, you have various ligands. In this case, in the silver case, 2 ammonias bind to the transition metal center. In the zinc case, 4 ammonias bound to the transition metal center. We have to keep track of the stoichiometry of these particular ions in solution because it's going to influence our equilibrium concentrations, and there's going to be exponents involved. So make sure that you don't forget about the squared value there in this particular instance. The reason we go through these 2 steps also makes our K really, really small. In this case, 10 to the minus 8. That allows us to use particular approximations. So we can ignore this 2x and this x right here, and we can do the algebra and solve for the concentration of x, and that's going to approximately be 3.7 times 10 to the minus 10th. So let's kind of take a step back and think about what this value means. We look at x in previous cases and we said x is the molar solubility. In this case, we don't even have any solids, so this is definitely not a molar solubility. Think about where x shows up. X right here is the equilibrium concentration of silver plus in solution. And if we think back to how I posed this problem, we asked for the concentration of silver ions in solution. So this 3.7 times 10 to the minus 10th is going to equal our silver plus. So this is what we were looking for. And again, it should not surprise you that this value is so small because we started with 0.05 molar. If we add enough ammonia, we're going to form this complex ion, and we're going to get a very, very low concentration of silver. So if our goal was to remove all the silver cations in solution, we've done an excellent job of that right here because that concentration now is really, 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 really small. Okay? There are several examples of these types of problems on the homework set that's posted on Carmen. Make sure you go through them and know how to manipulate these guys. Does anybody have any questions on these complex ion calculations? Yeah. In the question, it says that there is also 0.05 molar chlorine ions. Mm-hmm. Does that have anything to do with the algebra? No, it doesn't. That's kind of like a, I don't know, like a head fake additional information type of thing in there. If the only way that that would matter is if you had a large enough concentration of chloride ions and silver ions to form a precipitate. Okay? And in this case, since they're low enough, we can, basically it's kind of like saturating a solution, pulling those ions out.